Okay. So what did we talk about?
We're taking the limit as
The boundary condition, right? So
continuity.
yeah. So let's talk about work and energy.
And before we start that, can we just loop back around? When we found it to be the discontinuity to be sigma over epsilon naught.
Yep.
And after that, we went into voltage and kind of talking about that being important. What's the significance of that sigma over it? Because in the homework, it makes you do it for a sphere and the parallel, and it's all there.
Yeah. Equals what? Sigma over epsilon naught times normal, right?
Mm-hmm.
And then we also showed that this is potential is continuous. So now your question, I was just sort of setting a reminder of what we did. What was your question? The example we did?
No, it's like the sigma over epsilon naught. What does it mean? Like like the flaw,
yeah.
or you know.
Yeah. So, and hopefully I can draw this correctly. Yeah. So the electric field, let's say above, looks like this. So that means, in particular, the tangential component looks like this, right? And my normal component looks like this. That is from above. Now, for below, I know one thing already. I don't know how to draw my normal component of the electric field. But I already know the tangential component of the electric field should be exactly this. So from below, let me do it this way. It could be this. Yeah? It could be it could be, this. It could be that. So the tangential component should be this. If this surface did not have any charge density, then it would be exactly this, even from below. But if there's a sigma surface density on the surface, the normal component doesn't have to be this. So it can be something like, is that visibly smaller? Yeah? And that means this is E above and E below. These are vectors now. These are vectors. So that their tangential components are same, but this minus this in numerical value is sigma over epsilon naught. Is that clear? Yeah. I don't know if I should have made it shorter or longer even.
It could have even pointed still above the surface.
It could, yeah.
As long as it's discontinuous.
That is correct. It could even be pointing above.
Here's the thing, like, if you actually have, right, if you look at the difference between the electric fields from above and below,
Yeah.
right, you actually have the vector diagram of difference
Yep.
right there on the board.
Yeah,
right?
that's what it
The
is.
difference is the difference between the heads.
Yep.
And you know, of those two, the two lights, right? And you notice that points in the perpendicular direction,
Yep.
which is the normal direction.
Yep. The discontinuity is only in the normal direction. Does that make sense? Anything else? And potential has to be continuous. That means if you take a multimeter here and here, and then you bring it over here, it becomes just 0. Yeah. Okay. So now I'm going to talk about work and energy. In electrostatics. So work and energy mean many things to many people under many different contexts. So what do I mean here? You'll very soon see that what we're trying to do is assemble charges in a certain configuration. So the first one is easy to bring. There's nothing else in the universe. You create a charge, and there's no force acting on it. You bring it and leave it here and glue it onto something so that it's rigid. Now you take your second charge, and as you bring it closer, you're going to feel an attraction or a repulsion. So you have to push or pull. So you're doing work. So the question is, what is the cost of energy to assemble charges in a certain fixed electrostatic configuration? One charge at a time. Turns out you will see the answer doesn't depend on which charge was brought first. Regardless of how you bring the charge, the total cost at the end is the same. So we can, do it in any order. Yeah, that's what we're going to do. First of all, let's do this. Suppose, I don't want to make it look like a sphere. Suppose you have some charge over here. Let's call it Q. And then you're going to bring a test charge from infinity all the way up to some particular location. What is the work done? Well, work done is the integral of let me just use from initial point to final point. Initial point, it doesn't really matter at the moment, but eventually I'm going to pick it to be infinity. Bring it from far and assemble far enough. Okay. Well, what is the force on a charge? It's Q times the electric field. So I need a different Q, and I think Griffith uses an uppercase, oddly enough, here. So I'm going to use uppercase as well. Well, I'm bringing it. So what I'm doing is I'm doing work against this guy. This charge creates an electric field and imparts a force Q times E on this charge. So when I'm bringing it in, I have to apply an opposite force, so that it does. So if it's attractive, I want to make sure it doesn't fall in. If it's repulsive, I want to make sure it doesn't go out. So either which way, to bring in a charge and leave it at a certain point till I glue it maybe later on, I have to apply an opposite force. So this is minus QE dot DL initial final. Well, let's do this. Minus Q. I'm going to write E as minus the gradient of potential dot DL initial final. Yeah? So minus and minus cancels. And then I have initial final gradient V dot DL. Yeah? And I would have This is actually to assemble a charge, okay? Let me not assemble the charge at the moment. And then we'll start assembling the charge. This is just the work done by the electric field. So I'm sorry about that, minus, and this is nothing more than delta V. We have shown that, delta V, so that is minus Q V F minus VI. Yeah? And so that's what it is. So this is the work done. Negative, the change in potential energy. So this can be thought of as negative, the change in potential energy, where potential energy is what? Q times electric potential. Yeah. Just from there. It's negative the change in potential energy, so yeah. So electric potential has a meaning. What is the other? We hadn't really connected a meaning to the electric potential yet. We created the electric potential by simply saying that from Helmholtz theorem, it's the quantity whose negative of the gradient is the electric field. Now, this is one small step for algebra kind, but a giant step in sort of meaning. It's the potential energy per unit charge. That is what the electric potential is. Because remember from classical mechanics, you have the work energy theorem. And there are two versions of this. One is in general, the other is for conservative forces. And I know all of you are taking mechanics now, so I'll just ask you to recall, what is the work kinetic energy theorem? It's the work kinetic energy theorem. Work, network, is what? Net, I should say net. Huh? It changes? Kinetic energy work, kinetic energy theorem. They are the same. But for conservative forces, only for conservative forces, what is work? Almost.
Is that, I don't know, I want to say T minus 2. No, that's not it.
Which one? Here?
No, for the bottom.
This one? Work done by conservative force. I'm going to call Dr. Bankert up right now and say, your students are pretending to have never seen this. I know he has drilled this into you several times. Freshman physics. Negative, the change in potential energy, which is precisely what we have. The electrostatic force is a conservative force because there is an electric potential. Now, why did we define the whole thing with a negative? Remember in Helmholtz theorem, and I'm just randomly writing things now, just in terms of recall, any force could be written as negative the gradient of U plus the curl of W, right? This negative was not necessary. We just stuck it in because we found it convenient. Well, we don't know if we found it convenient. I just mentioned we found it convenient. This minus can be traced all the way back and trace down to here. We didn't have to put that in. And that is because we get this. Again, I'm not telling you why that makes a big difference. Yeah? But why? If you have a conservative force, what is true about the energy of a particle when it's moving under the action of a conservative force? The question is the answer is in the question. What is true about the energy of a particle moving? What makes a force conservative?
The energy stays the same.
Energy stays the same. Now, why is that the case? All of this somehow nicely fits in. If there are only conservative forces, then the net work done is the work done by conservative forces. So then, not then, I should say, if there are only conservative forces, then net work done is equal to work done by conservative forces, because that's the only thing that exists, which is delta KE on the one hand, and equal to negative delta PE on the other hand. Oh yeah, equal to negative delta PE. And then we have that delta KE plus PE equal to 0. Or and therefore we can call this the total energy. Kinetic energy plus potential energy. So and hence the term, the same term for potential energy and electric potential. The thing to remember is the electric potential is the potential energy per unit charge.
The analog is, right, the electric field is the force.
Yep, per unit charge. We good? Okay, so now, good? Now we're going to assemble charges. How many S in assembly? Yeah? Okay. So the first charge, let's say Q1, is brought to some location for free. There's nothing else in the universe. And then you take a second charge and bring it all the way over here. Q2. The distance, now I don't care about vectors anymore because I'll tell you why. We're talking about potential energy. The notation, the separation distance, I will write this as 1, 2. It's simply the distance between these two. What is the work done by me as I bring this charge? It's negative of the work done by the field. Yeah? So this is work done by, I don't want to say me, work done in to its final location. And this is because, remember, force applied to do this is minus Q2. Q2, not plus. Yeah, as I've just mentioned it before. So it is going to be Q2 times change in electric potential, Q2 times VF minus VI initial point is at infinity. When you have a single charge, its potential due to this point, right? So I should say also potential due to Q1. What is the potential at infinity? 0. Good. So the work done is nothing but Q2 VF, which is Q2 times KQ1 over. You see that? Okay. This is the expression that we need. Now what I'm going to do is do Q1, Q2, and Q3. My obvious notation, what is this? This would be separation. It's literally the distance between these two charges. What do you think this is going to be? 1, 3, and 2, 3. Yeah? Okay, so what I'm going to do is now, because I've labeled them 2 and 3, I'm going to bring 2 first, and then I'm going to bring 3 afterwards, and then so on and so forth. Okay. And you'll see that it does not make a difference. So first I'll bring Q2 in. Well, great, I've done that. K, Q1, Q2 over R12. Then I'm going to bring Q3. When I bring Q3, what is the potential it is seeing? Potential due to? And Q2. So I have K, Q3, Q1, R13, plus K, Q3, Q2, R23. Just for fun, because I don't want to write down, you should tell me all the terms. Suppose I bring a Q4. What are the, how many terms will I have? So this is the foreigner now. How many terms will I have to add? Another 3 terms. Tell me all of them. Q1, good. R4 plus K. Yeah? So you have to always include the previous one. So now we use a little bit of induction. We know how to do this. Let's write the general term. There are n many charges. K, Qi, Qj. Remember, in every case, there are two charges. So I'm going to call them I and j. And then I'm going to divide by their distance. And there are n charges, so I'm going to do I equals 1 to n. But if I did j from 1 to n, I'll be doing it twice. Yeah? So I could, it doesn't matter which one I use, I could use j greater than I to n. So that no combination is repeated twice. You don't want Q1, Q3, and then Q3, Q1. That would be counting it twice. So this is the formula.
You also
And
don't want Q1, Q1 too.
you don't want Q1, Q1 either. Yeah? But then I'm going to do exactly what I said I don't want to do. But I'll be careful. If you do it twice, you divide it by 2. So now I can do j not equal to I, just not equal to, and I equals 1 to, and k qi qj over ri. This is what it is. It doesn't gain us any big insight, but it's just a generalization of that. So one of the problems you'll do in the homework is I'll have three charges, and I'll ask you, and I'll tell you the magnitudes of the charges are 2 coulombs, minus 6 coulombs, 8 coulombs, and I'll tell you the separation distance, 1 millimeter or 2 centimeters. What is the total? And this is a problem you should long for because it's a no-brainer. You just plug it in. It's take home. You have the expression with you. Just make sure that you have all the terms. Okay, but we'll also be a little more sophisticated. So I'm not going to do that homework problem, okay, with 3 charges. I'll do a problem, don't worry. But let me simplify this a little bit more. I can write this as 1/2 I equals 1 to n qi. There's no j here, so I can do j not equal to I all the way. Well, j equals 1 to n, but j not equal to I, k qj over r I j. Yeah? And then I notice something. I notice that Qi, this is nothing but potential that Qi sees. Potential due to every other charge. Yeah? So I have a nice symbol for that. I will just call it V at the location Ri. So this is location of Qi. This Ri is the location of. So it is Qi times the potential at the point where Qi is to be brought in. So when you do that, you don't include the self potential. Qi doesn't see a potential on itself. What would be the problem if it did? it would be infinite, right? The distance goes to 0. So Qi doesn't see potential on itself. It's the potential due to the other charges. This is the discrete version. The continuous version what happens to sigma in the continuous version? It becomes an integral sign. Yeah. And I could write this as dq v. This doesn't quite make sense yet, but let me write this. Rho v d tau over. Oh, no, I don't need that. It is just rho dq can be written as rho d tau. And then if I wanted to, I could put in the expression for v, which I want at the moment. Yeah? So we will, let me box it. And let me make sure I unbox the versions. Yeah, no, this is the discrete version. This is the continuous version. We'll do this. We'll actually calculate this. So this won't be a mysterious object. It's not. You know how to do it, but we'll do it. Any questions so far? The dq becomes, what is rho? dq charge per unit volume. So dq is rho d tau. And I just cannot think of d tau as volume, but that's what Griffiths.
Is the reason I didn't change it to something like sigma dA because
You can. It's always easier to write it as a volume charge density, but in fact, if it is a surface, you can always use delta function and make it a sigma. And yeah. But we live in 3 dimensions, so just write out the 3-dimensional version. But it could in fact be a length or like a wire or a surface. Yeah. And there are many ways to handle that. In those explicit cases, you would just make it a lambda. Actually, you will not. You'll write rho as a delta function as needed, but you'll still have to integrate over all space. Yeah. But it might shrink the integral. Yeah. So I want to do this kind of problem, but it would be too easy if I brought 3 charges. 4 charges. I'm going to do infinitely many charges. I saw this problem, and I was kind of thinking about it last night. It's a problem from the textbook. Let me find the problem number for you. It's problem 33. So there is a charge over here, Q. And a distance A, this distance is A. All distances between all points are going to be A. There is minus Q. then over here, there is Q. And then,
There's a little extra up there, we didn't put it over there, did you?
I'm sorry,
Did you do that?
that's from previous histories of things past. How many charges are there? Infinitely many now. And the question is, it doesn't matter which one, find the work done to assemble one charge. Assume everything else is already brought there for you. So I'm going to write the work done to bring Q with just these two guys first. Then I'll write it with these two guys, and so on and so forth. So it is minus 2 k q squared over a. Correct? Is that correct? It's q times the potential due to this, which is kq over a.
Wait, who's going where again? Is the negative, you're bringing the negative?
So you're imagining that one in the middle is
Yeah.
missing.
Oh.
And
Yeah.
you're gonna bring that in from
Yeah,
infinity. while
so
all the
this
others are
one,
there.
yeah, I'm going to bring this guy in. So let me write it first time as two terms. So it's q times the potential due to this charge at this point, which is k times negative q over a.
Okay, yes.
One more time, q times k times negative q over a, right? Plus,
And then,
tell me what it is, q times kq positive over what?
2A,
2a plus q times kq over,
negative, wait, isn't there-
no, these are both positive.
Oh, okay, all right, yeah.
Yeah, so then, remember all of these come in pairs, so I'm going to do 2k q squared over a. What do I get? From here and here I get a minus 1.
Yeah.
And what do I get? 1 over 2 minus 1 over 3. I'm going to bring the minus out. I like the first guy to be positive. Minus 2k q squared over a. 1 minus 1/2 plus 1/3. Are we good? Did I make any mistakes? So then I would thumb through my calculus 2 chapters, or in this day, I would Google it. You type any sequence in, it'll tell you what the series is. Back in the day, you would look up the Russian table of integrals, or the CRC handbook or something like that. Or if you had recently a course in infinite series, you might even remember what it is. But turns out, for me, it came with a search. Natural log of 1 plus x is nothing more than 1 plus x over 1 plus x.
The one is missing. No one on the right-hand side. Of your expansion, the natural log is 1 plus x.
Yeah.
The one.
Oh, right, the
no
one
one
is
there,
missing. Yeah, yeah. X plus x minus x squared over 2 plus x cubed over 3. So this is nothing more than what? natural log of 2. I would have been happy with this in this class, but
Add it by hand.
I'm sorry?
Or just add it in by hand.
Yeah, no, you don't have to add it by hand, but there it is. This is the work done in assembling this charge. It's easy to see that one should be missing because when x is 0, natural log of 1 is 0. Yeah, it's a good catch. That is, if you look at it, I don't think that's the answer Griffith shows. Maybe it is. He just writes it as alpha and says, your problem is to determine alpha. It's natural log of 2. Yeah? Is that clear?
Just kind of doesn't take an infinite amount of work, right? Infinite amount of charges.
Right. No, but that's the work done per charge.
Sure. Okay.
So the other infinite amount of work has been done.
Yeah.
Yeah.
How much more work
Yeah.
on top of the infinite that has
Yeah.
already been done for you?
Yeah. It's a silly problem, but it also tells you, how these Taylor series are important, how infinite series are important. And you wouldn't remember all of these necessarily, this series in your head, but if you use it frequently enough, there may be some series that you use in your problem that you're studying. You might remember some of it. And every time you don't, you go back to your book and thumb through the few pages and get a sense of what's going on. But there are so many infinite series and so many expansions of so many functions that no one remembers all of it. Legend has it that Richard Feynman wanted to know where all the integral tables came from, so he took out some time and he worked all of it through and reconstructed tables that hundreds of people had compiled, put together. I don't know how anecdotal it is, but I'm not competing with Richard Feynman. Are we good? But your homework problem would be 2 or 3 or 4 charges in this category. Remember, there's an integral version of that. We'll be using that as well. And this can be massaged to a nicer form, which I'll do so the next time we meet. I hate to start a new topic